Today we're going to be looking at the Wilcoxon signed rank test, just as an example of a non-parametric test. Now, technically, inferential methods concerned with parameters are called parametric methods, but those that are not are called non-parametric methods. However, common statistical practice is to refer to most methods that can be applied without assuming normality as non-parametric. Thus, the term non-parametric method, as used in contemporary statistics, is somewhat a misnomer. But we're going to look at this particular one and what happens with the Wilcoxon signed rank test. It's going to be based on not that the distributions are normally distributed, but that they're somewhat symmetric. So we're going to actually look at an example and see how the Wilcoxon signed rank test basically works. So I take this example from Weiss's statistics book, and we're going to look at the weekly food costs. So U.S. families back in the day, with a family of 4, spent about $157 per week on food, much more expensive now. 10 randomly selected Kansas families of 4 were selected for this particular study. And they got their weekly costs, and it's noted there in the data right here. Now, we wish to show the average cost of families for Kansas is less than the national average. So we're looking at the hypothesis test of mu equal 157, which is the working null hypothesis. You know, correctly speaking, if we were to do this, and mathematically it should be greater than or equal to in the null hypothesis. But we're going to look at the working null hypothesis, and the worst case scenario, the hardest to prove, would be the 157. And the alternative is mu is less than 157. And again, remember, we're assuming, and when you look at the data and actually do a stem and leaf or something like that, it looks relatively symmetric. So the first thing that we're going to do, so I'm going to create a table. And in the table, I'm going to have these costs. I'm just going to write the data. So I'm going to write 143, 138, 169, and so forth. So I'm just going to write them in this first column. So I write them as I saw them. The next column is going to be the difference, my x value from the value in the null. So I took 143, subtracted it from 157, and got negative 14. 138 minus 157 got me negative 19, and so forth. Now what I'm going to do is take the absolute value of these differences. So if I call these the differences, I'm going to take the absolute value and make a column for that. So I'd say absolute value of negative 14 is 14, absolute value of negative 19 is 19, absolute value of 12 is 12, and so forth. The next thing I'm going to do is rank my absolute values, looking at that absolute distance, looking at who was the furthest. So I would say the furthest away when I look at this would be 22, excuse me. And the closest would be 2. So I'm going to rank not from the furthest, but from the closest to the furthest away. So 2 would be ranked 1. There's nothing closer than 4, so that's ranked 2. Nothing closer than 5, that's ranked 3. Then I look, is there a 6? No. Is there a 7? Oh, yeah. There's 4. There's 8. Then we look, is there a 9? No. Is there a 10? No. Is there one that's 11? And so forth. So we do this for all of these, and we put them in ranking from smallest away to largest away. So now what we're going to do is put back the sign so that we know that, yeah, it's 7 away, but is it 7 away to the left or the right of 157? So we're going to put, and that's why this is called the signed rank test. So the signed rank of our, of these distances right here. So 7, it came from being negative away, so that's negative 7. This is negative 9. This would be positive. This would be negative. And so forth. And I'll write all of these in. So now we have all the signed rank distances away. Now, think about it. If this distribution truly was symmetric and the Kansas spending for food for a family of 4 was the same as the rest of the United States, you would think there'd be the same amount, arithmetically to the right as to the left, as many positives as negatives. So what we would do is we would look at, if I was ranking all the way up to 10, that would give me 55. And I would expect that half would be positive, half would be negative. So half of 55 would equal 27.5. So I should look at my positive rankings, and hopefully they would get me 27.5, and the negative rankings, if I took their absolute values and added them, 27.5. If the sum of the positive ranks is too much smaller than this, then that's probably not a good, that's not good evidence, or it's I would say, to say it again, it would probably be good evidence against the null. So let's look at our positive rankings. It's here, here, and here. So look at our positive ranks. 6 plus 2 plus 1, 9. Ugh, that's not even close to 27.5. So again, looking at 9 is so much different than that. That's not real good for the null hypothesis, that this is probably going to be evidence to support the alternative. But let's take a closer look at that. So we're going to use the symbol W alpha, and that's going to denote the W value that has an area or percentage alpha to the right of it. So in other words, looking at this is going to be this area here. Now, we have to get these numbers from a table, a special table, and it's in the back of most introductory stat books, so that we can get this quote-unquote critical value. If I'm on a left-tailed test, like the one that I'm in here, I'm looking for this. And then for our two-tailed, so this is right, this is left, and this is two-tailed. Of course, we're going to be looking for W of alpha over 2. And this, because this is alpha over 2, that's alpha over 2. 1 minus your alpha over 2. And so we have to go look in the back of the book. Since we are in a left-tailed test, we've got to find out how to find our critical value and then look at what's happening with our problem. So with our problem, we're looking at n equal 10. That's this right here. And let's say that we were doing our test at a 0.05 significance level. Because we're in a left-tailed test, we have to look at 1 minus our alpha, or 0.95. But you look at it and you say, I can't find that. What would I do? So we have to find out, how do I find my critical value? And this is how we find it for a left-tailed test. For a two-tailed test, so for our sample size, we'd put a 10 in for n. So we'd have 55 minus W of 0.05. Well, sample size of 10, W of 0.05. So I'd say 55 minus 44. So my critical value is 11 for my left-tailed test. So what exactly does that mean? So with that equaling 11, what I have to do is I have to think about that this is my critical value. The rejection region consists of all W values less than that because I'm in the left-tailed test. So all my test statistic values that would be to the left of that would tell me that I should reject the null hypothesis. So if my W was 9, remember, in here it's 9, I would say if my W is less than my critical value, if my W, from my null is less than my critical value, I'll reject the null hypothesis. Well, I have a 9. Is it less than this critical value? It sure is. So that gives me enough evidence to reject the null hypothesis at a 0.05 significance level. So we would say at a 0.05 significance level, the data provide sufficient evidence to conclude that the mean weekly cost for a Kansas family of 4 is less than the national mean of $154. So that was a really fast look at just another technique we could use to do a hypothesis test if we could not establish normality, but just symmetry, whether it's triangular, uniform, something like that. With a small sample size, we could use the Wilcoxon rank test. Now, something to note, you could always use this since this is talking about symmetric distributions. You could use the Wilcoxon in place of our regular parametric test where we establish normality, but it's not as powerful as our parametric test, such as a Z or T test. But it does require less computation. So some people tend to like using this quickly, and certain statistical software packages, when you do tests, will you can do the Wilcoxon signed rank test relatively easy. So again, just a quick look at a non-parametric test.